Hi, Alexander, welcome.
Hi. I hope you can hear me well.
Yes, I can hear you well.
Wonderful.
So let me present you, Alexander, and then I'll let you start with the presentation, okay, for the keynote.
Yeah.
Okay, Dr. Alexander Dockhorn is a junior professor at the Institute for Information Processing of the Gottfried Wilhelm Leibniz University in Hanover. Following his dissertation at the Otto von Guericke University of Magdeburg, the OBGU, he worked at the Queen Mary University of London and later came back to the OBGU. During this time, he studied artificial intelligence in general strategy games and began working on abstraction methods to facilitate more efficient search strategies in complex applications. His current research interests include model-based decision-making, transfer learning, and explainable machine learning. He's an active member of the Institute of Electrical and Electronics Engineers, the IEEE, for which he serves as chair of the IEEE CIS Games Technical Committee and the Summer School Subcommittee. So, Alexander, you're welcome. You can go ahead with the keynote.
Thank you very much. Yeah, it's an honor to be here, at least virtually. And I'm very sorry I need to speak English because my language teacher told me I should put more time into vocabulary, but actually I was more involved in games and this continued for all my work life. So that's why I'm here as well. It's just that I can only speak English with you. So you already heard something about my scientific career, so I don't need to give you much more information to it. The only thing that I want to highlight a bit is that I'm currently chair of the Games Technical Committee, which is probably why I'm speaking to you. So what we try to get out here is that working on game AI or games in general has more benefits than just game playing, but also we can advance so much more in the machine learning domain that there's really much more use to it. Additionally, I have been heavily involved in game development myself, so it's not just work life, but it's also a hobby and a passion to develop games. And to study how game AI is being developed actually motivated me for my computer science career. So that's why I picked up this course of study. I hope that in case some of you have not been involved in games, I can transport some of this passion throughout my talk. And even if you're not interested in games itself, there will definitely be something for you on the talk as well, since all of these rely heavily on machine learning methods, and it's just another application domain, which can be interesting, but you can replace it with other applications partially. So my research focus itself is the applications in game AI, and I search for dynamic processes that I want to analyze. I check for causality in models that I learn. I'm heavily interested in transferring knowledge in between different games and game environments, and the models should generalize as much as possible. All of these research topics are highly interconnected, and I will show you throughout this talk what I mean by this by introducing them step by step. So first of all, why do I study game AI? And in general, if we think about AI or computational intelligence, we refer to the ability of a computer to learn a specific task from data or experimental observation. Now, if we are not too focused on games itself, then we might think of self-driving cars or parking aids, or we have an automating production pipeline. All of these are perfectly valid and interesting tasks, and they have huge benefits. But the problem with them is if it comes about studying machine learning algorithms with them, we have real tasks that are hard to set up. And during the learning phase, any failure of the algorithm might have considerable cost, such that if we apply machine learning, it is likely to not be performant from the beginning on, and then we have some risk involved that we would like to minimize as much as possible. Furthermore, if we want to study characteristics of an algorithm, we cannot just simply modify the real task, and therefore we cannot easily study the underlying characteristics of the algorithm itself. So how would it scale with certain applications or with increasing the input and output space? And here games come into play. They become a benchmark for us in terms of machine learning because they simulate many real-world tasks, even not on the most detailed level, but the solutions can likely be transferred back to some real-world environments, such that we take a real-world task, we simulate it in terms of a game, we train and optimize a machine learning solution, then apply it to the real world, and finally we can test and evaluate the performance of the algorithm. So games also offer us quantifiable goals and a controllable difficulty and provide us with large data sets, most often from human players. All of these aspects are highly relevant when we think about training machine learning models, and therefore it's just a wonderful domain to work in. Furthermore, digital games are fully accessible to computers such that we don't need to transfer in between solutions, and games are just fun to study. That's a personal motivation, but I hope it will be yours as well. So with a slightly boring take on game AI, we shortly look at the history of game AI, but I promised I really make it short. So if we look at solutions, they are first have been motivated by mathematically solving a game, such that we find the perfect action for each possible state, which has been done for backgammon. We just can determine the whole game space and then determine the best action for each action. You might know the game tic-tac-toe, in which it's fairly easy to identify the best action, and this is what I mean by mathematically solving a game. Then we had rule-based abstract approximations. So we have expert knowledge that we get into our solution, and these expert knowledge can help us to guide search algorithms to solve problems in real time. Such things have been implemented by Deep Blue, the famous chess AI, which beat the world champion Kasparov in 1997 and is still up to date to some degree. But it has recently been overtaken by learned heuristics, for example, by AlphaGo, which achieved the massive task of playing Go, an extremely complex state space of a game, and beat the world champion in 2016. So we have some transfer in between methods. We first try to solve them completely, and we become more approximating step by step. If we look at the most recent successes, we have many companies investing into research on game AI because of the properties that I mentioned before. And we see a move from simple to complex domains, from single to multi-agent scenarios like poker, and perfect to imperfect information games in which many details are hidden to the player and need to be inferred during the time of the play. Also, we had elements of cooperation included, and all of these things make games much more difficult, but also more realistic in terms of transferring them to other applications later on. I don't want to go into the details of all of these game solutions. That's it with my history. But if we look at the development of these systems in terms of machine learning, we always became specialists first, and then we tried to generalize these algorithms to other domains as well. So the solutions most often started with expert systems, which derive a solution given expert knowledge, and then we try to automatize the simple processes. Then we added sub-symbolic information like fuzzy or probabilistic systems, which help us already to generalize patterns from the expert knowledge, and then we can improve our performance more and more. Given enough data, we had the ability to apply machine learning algorithms, which also scales with the amount of processing power that we have available. And since both of them are often available now, machine learning is more and more applied to game AI, such that we can detect patterns automatically, which has previously been provided by experts. And we see the development of more and more meta-learning algorithms, which use machine learning to optimize the training of machine learning models, to make them more efficient in terms of, for example, the parameter optimization, or in the context of neural networks, the architecture selection. What interests me most in this move from specialist to more generalist learning behavior is the missing step to artificial general intelligence. It describes a generally applicable AI algorithm that adapts to a given task. And this adaptation is the main problem. With all the solutions that we discussed before and all the successes that have been found by the major companies, it's that they retrain for every game. They don't have a solution that works on Go and then they just make a small update and it can suddenly play chess because the same concepts are used. But it needs to really start from scratch. And that's what I want to minimize as much as possible to become more efficient. So how to develop a game AI? Most of you might already know that there's the agent environment interface, which generally describes the task in which we learn. And it's a general framework that includes an agent that interacts with an environment by applying actions and receiving a reward. The reward tells the agent how good it performed, and therefore the agent wants to optimize the choice of actions to maximize its reward over time. And this general framework describes many learning tasks and is the foundation for all the work that is shown in the remainder of this talk. But let's look at which solutions are possible. So if we consider a simple maze, a simply connected maze, which is a certain mathematical attribute, then you might be aware of the expert rule to put your right or your left hand on the wall and then just follow along. It will always, in simply connected mazes, bring you to the end of the maze. I hope this didn't destroy the fun of you for going into mazes. Just don't apply this rule if you still want to have fun. But I can promise you that it doesn't work out for all mazes, since the simply connected maze is just a very simple type of maze that we don't see often in real world, since humans get adapted to it pretty quickly. But even for more complicated mazes, we can choose more complicated rule sets, which always guide us to the finish line, which is nice to escape maze, but a bit sad and disappointing that something so simple already suffices. However, there are more complicated tasks in which we not just want to reach an end, but we have many subsequent actions that we want to take and sub-goals to reach. So in game AI development, we have seen the emergence of behavior trees. A behavior tree combines multiple expert rules by condition, sequence, and selection nodes. And game designers really like about this concept that they can easily interpret the overall structure and follow along the agent's decision process. That's an advantage of such tree-based approaches. But the problem is their complexity doesn't scale well if we want to design them by our own. So machine learning is still relevant. It's just not that present in game AI development. And the reason for this, if we just think about the game development, is that the expert solutions and the rule-based systems are just cheaper and faster to develop. They are simpler to debug, and the designers have more control over the final behavior. Furthermore, there's just no need, since psychological studies showed that players expect to win against an AI opponent, and therefore having a very strong AI agent can be disappointing for many of the more casual players. And for the remainder, we have player versus player modes where can they really challenge themselves by playing against other real human opponents. So machine learning requires experience and costs money and time, and both of them is a very valuable resource in game development. However, for studying properties of machine learning algorithms, they're still worth the effort to go through games, since we have so many nice characteristics, like we can model the game world as we would like and study the machine learning algorithm under the conditions that we provide. Therefore, let's check out how machine learning is applied to games. There are two fundamental problem classifications. Either we want to learn which actions are good, or we want to learn to anticipate future states, or we have some information to anticipate future states, such that we can use the result of this anticipation to find out the best possible action to use in the current moment. Both learning approaches, or both learning goals, allow us to define algorithms on these dimensions. And therefore, the algorithm classes reinforcement learning and simulation-based search have been developed. Reinforcement learning aims to approximate the expected return of every state and action of the environment. Therefore, the performance heavily depends on the available training time, because the agent just goes through numerous observations and then tries to average in total. There are different clever processes on how to do this average, but all of them rely on the same fundamental principle: learn by repetition. In terms of simulation-based search, we have the game's rules available at our hand, and therefore we can predict the outcome of our actions. And given this prediction, we can determine which outcome we like most. So we can select our action given this online observations that we do. So the performance depends on the available computation time during the evaluation, because predicting multiple action sequences gives us a better indicator of which action is the best. So if we focus on simulation-based search first, here's a schematic overview of how it works. We have the current state and the game model as an input, and as an output, we get the action with the highest win rate. This by just determining the conditional probability of success for every given action at the root state. The problem is, how do we handle games or environments in which we don't know anything about the game model? Or how can we infer the root node state in case we cannot fully observe it? Both of those are perfectly valid problems in other applications, because if we think of robotics, then our robot might just not know what it interacts with at the next moment. It might even not be possible to observe everything because objects are partially hidden, and therefore the agent needs to guess its future transitions. So there's a lot to do if we want to apply simulation-based search to other applications. And in games, we have these models available, so we can take them away and let the agent learn a model and then compare the result to get better understanding of the agent's learning characteristics. If we consider such a game model, how it works, I want to present a more detailed example, which is well known. Here is an excerpt of the chessboard. And basically, with every transition that we see on the edges, we have one action being played out. And then we want to optimize the action by maximizing our value and minimizing the value of our opponent. We can also apply it to other domains. For example, on the left, we see Mario, and he's planning different action sequences, which are all drawn in as red lines, and then he can choose the outcome that he likes most. Similarly to autonomous parking processes, where we want to put the steering wheel and our gas such that we get into the parking position without putting another scratch on a car. And all of these behaviors are pretty natural to humans. It's just a question of how can we apply the same to AI if the AI doesn't know anything about the environment. In reinforcement learning, we have different paradigms in contrast to other machine learning algorithms. At first, we have no supervisor. We only get a reward signal that tells us something about the value of our actions, but this feedback can be very delayed. So we don't know if the reward is caused by the latest action or by something before. And we have a very time-dependent and sequential learning task, since any action that we take influences the remainder of our game, and therefore it might impact which data we can observe. Now, I already mentioned that there are different algorithm types that learn given this information. And one of the most prominent ones is the Q-learning algorithm. It approximates the value of every state and action given observation. And here I've shown you one example. It's a single path that has yielded to the results that we want to reach. And then we can backpropagate the information to determine the value of an action. Due to this backpropagation, we are less and less sure about each of the action's values, so we get less information the longer the path is. But we can repeat this process many, many times, and then we get an ideal indication which action to take at which state. Now, the classic approach used such a tabular method. So for each state, they directly indicate the value of each action. The problem is if the environments become too complex, such a tabular method would just require too much memory, and it would require too much time to explore the environment. Therefore, deep reinforcement learning replaces this table with a deep neural network that just approximates the value of an action given the information of the current state. Here are some examples of reinforcement learning in which we control a set of actuators to reach a given goal. And as mentioned before, such algorithms can be used in robotics. And here we see some typical benchmark scenarios, but games can be more complex than these simple benchmark scenarios. And here we see that the state and action spaces are very large. Therefore, the parameter space grows with the complexity of the environment, and the training time scales very badly. So even if the huge companies are able to learn models that can play these games and much more complex games than the game shown here, it is most often not feasible for universities to replicate the same results, since it just costs too much time, energy, and money, and there's too much to do on these. But I don't want to discourage you, because there's more to it. So there are more general solutions like deep reinforcement learning, which approximates a function, but it can also take quite a while until it's trained. And there's prediction-based search, a framework in which we want to train, in which we want to learn to predict future upcoming states, such that we can apply simulation-based search methods. And as a comparison, deep reinforcement learning often has many model parameters and requires large amounts of training time. But once trained, the model can be applied reasonably fast because the induction time in neural networks is very short. Nevertheless, the inspection of the model's decision process can be very tedious. So it can be hard to understand why the agent behaves in a certain way. And in terms of from the perspective of a game designer, we are not really able to direct the agent in a direction that we would like to have. Then we have prediction-based search on the other side, which requires large amounts of runtime while being applied, but it does not require to be trained at all. So if we develop a game and we change it, we can just apply the same agent once again, and it would work to some degree. I mean, there's always information that we could still learn, but it's not required by the method itself. And the found solutions can most often be better interpreted because we have the whole search tree available, and we can review why the agents chose to follow along a certain path. So if we look at recent successes of game AI, we see that many of them use deep reinforcement learning or a combination of deep reinforcement learning and search trees. However, all of these solutions are still highly specialized, and they don't generalize to other games. So a challenge that I'm most often interested in is one that I want to introduce to you now. It's general game playing and general game learning, in the sense that an algorithm is not just able to be retrained on each of the games, but to transfer knowledge in between them. And in general game playing, we consider an agent is able to simulate future time steps, but then is fairly able to decide which action is the best to take. And in general game learning, we even take this information away such that it first needs to learn how to predict future states to better choose its actions. And here, search-based algorithms would require to learn such a forward model in domains in which they currently cannot be applied, like putting a robot into a new kitchen, which it doesn't know at all. Then it needs to first learn where it can find all the cutlery. It needs to learn where to find the pan to cook an egg, for example. And to study these things, we need a framework. One framework that I based my work on is the general video game AI framework. It offers access to more than 100 games while giving us access to their forward models. Having access to the forward model means we can compare a learning approach with an approach that already knows everything about the framework. We know that in this framework, search-based approaches have worked incredibly well. They are capable of playing many games to the same degree as humans would do, and they are able to be successful in most of them. Nevertheless, the games are very diverse. So we have varying game characteristics like the type and number of non-player characters. We have different resource systems and different reward styles like dense and sparse rewards. And we have games that highly differ in the terms of determinism and non-determinism. All of these are things that are challenging characteristics to be studied on their own. And with this single framework, we can directly study the behavior of our machine learning approach under all of these characteristics by isolating them in each of the games. How did we approach this? So the forward model learning approach wants to apply a search-based solution, but it requires a forward model. So we try to learn to predict the upcoming state of an environment, just given the information of the current state and the agent's action. And we would like to do it on any possible environment, but here for now, we focus on games that fulfill the Markov property, meaning that only the latest interaction is relevant for this prediction. We can easily scale up. The problem with scaling up is that it just requires much more training time with every additional interaction that we would like to take into account. The requirements for the final model that we would like to learn to predict future states are that the model needs to be highly accurate. Otherwise, the predictions would be basically useless. So we don't get any information on the quality of our actions. We want a model that can speedily be applied because tree search algorithms scale with the number of rollouts that they can do. And having a fast model would allow us to do more of them. We want a model that is reasonably small, such that it can be easily trained. And at best as possible, it should be interpretable and reliable. But the last two things, interpretable and reliability, are just the icing on the cake. So all the other ones are definitely required to apply a prediction-based search. And the other two are additional benefits that make it so much more usable if we can have such a model. So how to approach this problem? It's basically a classification or a regression task. We get the current state that the agent observed, we know which action it took, and we can observe the resulting state. So each of these observations is a single training instance, and then we can use any classifier or regression model to learn a forward model. Problem with this is that it's just not very efficient. But we can make use of expert information or higher complex models. So an implementation of the end-to-end solution would be to just put a neural network in the mid of it. We put the current state and the action as the input layer, the output layer is the resulting state, and then we would already have a forward model that could be trained. Problem is, it just includes so many training examples that it's hard to fit it in reasonable amount of training time. So we need to make assumptions on how to make this model more usable to reduce its model size or model space and the number of parameters that are used. And one assumption that can often be found in many prediction systems is the decomposition as a pattern. Here we assume that sensor inputs can be modeled independently, such that for each different sensor input, we could have a single forward model, which, for example, predicts the movement of a single car on the street. If we look at a full crossing, then we would have one model for each of the cars, and then we can predict their next movement to predict the state of the crossing at the next time step. That's a reasonable assumption in many cases. The problem is there will be dependencies that we ignore using this method. So what would be even better is to have an optimal decomposition for the current time step and for all the sensor inputs that we could find. Problem is that finding an optimal decomposition is once again a heavy learning task. So we would like to have reasonable independencies included, and that we just need to optimize a little without putting the burden on us to optimize over the space of all possible independencies. And one assumption that has often been present in games is the local dependency. Things that are locally close to each other are in relation with each other. This is an expert rule. So similarly to approaching other machine learning tasks, we first applied expert rules to finding optimal decompositions, which yielded the local forward model. The idea of the local forward model is that we have a structured representation of the state, and for each element, we can define a similarity or distance function to the other elements in the state representation. And the semantics over these different elements don't change. So as long as they look similarly, we assume that they also behave similar. The last assumption is not required, but it makes the learning once again much more simpler and is reasonable in game AI. So in terms of applying such a local forward model, we have the game state of a game. We define a local neighborhood, which is a pattern that we can choose. And then we can extract this pattern for one or for all possible positions. And for each of the extracted positions, we can have a single model that predicts the next state of this position. To get the next state overall, we just need to aggregate the independent predictions of each possible state, which is the same as predicting each car of a crossing independently, and then just aggregating the information to get the final state of the street. The local forward model has allowed us to learn models for many possible games. And if the pattern that is used as an input, so the local neighborhood, is the same, we have observed that even the patterns can be transferred in between different games, such that, for example, in this game here, we can push a block, and the push movement is exactly the same in this as in other games. So once we have learned a forward model that can represent pushing blocks, we can move the knowledge to other games and play and learn them more efficiently. We have applied this in terms of a prediction-based search, which starts with no information and just observes previous and current state pairs. It uses this information to learn such a forward model, and given the forward model, it predicts the upcoming state and selects an action that it wants to apply. Then it can observe what happens after it's applied this action. And given the difference between the next state that we observe and the state that we predicted to observe, we can improve the model of our forward model over time. We applied this learning scheme to the set of GVGAI games. And we have seen that in most of these games, we can learn highly accurate models, which predicts the future state with an accuracy of around 90%. This was mostly enough to play many of these games successfully. And we further looked into the games that we played well and the games that we didn't play well, and grouped them using a hierarchical clustering. So only looking at the performance, we can see games of similar characteristics being represented, yielding a similar performance of our agent. And these games include, or these game types includes games of sparse rewards, which are generally harder to learn because we have very delayed feedback for our actions. We have maze-like games, which are fairly simple for simulation-based search agents because they can easily explore their state space. We have long-term planning games, which are the same style, but are a bit more complicated. And we have games which include randomness, for example. And in between these categories, we have seen that we can transport patterns from one learned model to the next game to simplify the task, or at least that patterns are fairly similar in these cluster groups. Now, using the information of the forward model to quicker learn how to play a game or to generalize information is just one way. But the complexity of these games didn't allow us to study abstractions of the state and action space. And this is why we have focused to develop a new framework, which is the general strategy games framework called Stratega. It's a single framework which allows to study turn-based and real-time strategy games and to configure those to your liking. So we have a single configuration files in which each component of a game is being defined. And therefore we can apply this to many, apply our algorithms to many different variants of strategy games. The framework itself has been implemented with high execution speed in mind, such that we can make the forward models accessible and really make use of forward planning agents. And due to a rich set of debug options, it's much easier to develop than in other game frameworks. If you've never heard about strategy games in terms of turn-based and real-time strategy games, this is a one-slide overview of what happens. We have two players playing against each other. Those try to take control over different buildings, which give them access to resources or training units. Units need to traverse different terrain types, which each come with their different challenges. And the units themselves are used to mostly play war scenarios. So we want to attack the opponent and defeat him as quick as possible. Now that's the underlying framework, but there can be many different game modes to be implemented in the framework itself. And we used it to study these learning methods under games with much higher complexity. The problem with learning the forward model is here that the forward model itself can already be very heavy and slow because it needs to take care of so many different things at the same time. So the research questions that we posed for us was, how can we simplify these models to only the minimal expression? Is there some kind of approximation without losing too much accuracy? Can we base our decisions only on partial information? Because some of these games just include information that we don't need to take care at every moment. And can we base our search on such simplified states at the cost of accuracy? And then how high is this cost? Would it be worth it? Or is the simplification just too much to handle? So one of these simplifications is called action abstractions. In these strategy games, we have highly complex action spaces because we control all the units at the same time. And each of the units usually have 10 to 100 actions in a single game state. So it just explodes. And using search-based approaches has the problem that a flexible solution would use the original action space, but due to the number of different actions that we can use, we cannot search very deep. the most simple solution would be to use a greedy agent, which ignores all the other information and just goes through the most promising path. An action abstraction introduces something in the middle. We have multiple greedy agents which can be considered, and therefore we span a simplified tree. So we cut all the connections to states that have not been proposed by greedy agents, and we concentrate on the remainder. So a portfolio agent uses a collection of script, and a script is once again just an expert rule. The expert rule itself could be like attack your closest opponent. So if a unit has an opponent in range, it attacks it. Otherwise, it walks closer to it to attack it in one of the future time steps. This is fairly simple and can be easily communicated by experts, but we can learn other rules and scripts by reinforcement learning, for example. If we once have multiple such scripts and behaviors, we can combine them in a set called portfolio, and the portfolio agent then searches the best script to select its action, instead of just searching for the best action among all the possible actions. Questions that need to be answered would be how to effectively search through the script space, how can we compose our portfolio, how can we optimize it to reach better performance and diversity. And there are several algorithms which use portfolios to be efficient in their search task. Another approach to abstraction would be the game state abstraction, in which we use the information of the state to create an abstract representation which allows us to merge multiple states which are similar with each other. Here's an example of nodes with two properties, color and shape. And this allows us to group nodes by similar color or by similar shape, or we could come up with an even higher dimensional representation, which allows us to group them more arbitrarily. The game state abstraction simplifies the game state considerably. In this example, we had 6 states as child nodes, and we have only 3 merged nodes in both examples, left and right. So a game state abstraction can help us in our search, but how do we encode it in an environment that is not representing us with the same information at every game state? Because over time, we might produce more units, we might uncover new elements on a map, or we might build a building, and therefore our game state changes over time. So we used component-based representation in which we sort by attributes. So we sort all the health values together, we sort all the attack values and all the heal values. And all of these information can go as different heads into a neural network, for example, which processes this information. Or we can just mix and match the information that we use and ignore some parts of it. For example, if we want to control a healer, we only focus on health and heal values, but we don't need to focus on the attack values. If we want to control a knight, then we would focus more on the attack value itself and not on the heal capabilities of a unit. So the game state encoding, making it more abstract and more condensed, allows us to have a more flexible pattern identification to let the agent learn which of these game state information is really relevant to my representation. And this makes it reusable, because depending on the task, we can use different abstractions. But if we optimize for several games, we can reuse some of these abstractions. Here's an example for action abstractions, in which agents on the first game learned to use the same abstraction because it was the most relevant one. So each of the black cells signifies if an abstraction has been used. And we can see that, for example, in this game, attacking the weakest opponent is the most simple and most successful strategy. But the more successful agents include further abstractions into it. So they also choose to attack the closest opponent or to use some special abilities. In the game pushers, which is represented in the middle, we see that it is more diverse what the agents do. And especially the best performing agent uses completely different combination of strategies in his own behavior. And in the game healers, nearly each agent had a completely different representation of its action space and played differently. But still, they have similar performance. So while approaching the problem from different angles and learning this automatically, they identified multiple behaviors that can be successful. Here's a visualization in which we defined different dimensions of the agent's behavior, and it shows two solutions of our diverse set of agents that we produced, where the first one is just using melee units to be very aggressive in its movement, and the other one used a more defensive strategy relying on ranged units. So creating like a wall of units to attack everything that's coming close to us. And the melee strategy had a hard time of getting into it, but was successful against some of the agents. So that sums up how to create diverse agents, but what we study at the moment is how to produce such an abstraction while the agent is running. All of the previous abstractions have been pre-trained. So it requires some amount of time to identify which of these abstractions are really useful to the agent. And this can just be a costly method to do. But what we currently study is how do we abstract the game state and actions, the game space and action space while the search is running, such that we see how the tree grows, here by the example of Monte Carlo tree search. And given the information that we receive, we group nodes of similar reward together. This node grouping allows us to explore more efficient, and we can group iteratively. So, for example, every 100 steps that we simulated, we can group one more node together. We've seen that at the end, it is useful to break up this grouping and have a final refinement phase. But at this stage, the state space has much better been explored than only using the original game space. So using a dynamic abstraction can really boost the performance furthermore. Now, finally, to conclude all these different observations on abstractions and model learning, I have seen that, especially in my work, game AI has been very useful as a common benchmark for machine learning tasks, because we have applied these algorithms to completely different tasks as well, which are not any related to game AI, and they still perform very, very well because we understand their characteristics good. Then we have seen similar trends in research with this movement from symbolic AI to sub-symbolic AI to machine learning guided AI solutions, and solutions that generalize better and better. And in terms of the game AI developments that I push forward with, we have seen that learning such forward models can be very efficient in learning how to play a game. And the final model can often be transported to other domains to make the solutions more general. And even if we don't base this generalization on forward models, abstractions that are based on game state abstraction or action abstraction can also be a powerful tool for improving the learning to make it more efficient and to transport the knowledge to other environments. And a friend of mine has created a wonderful vision of how game AI could develop over time. She presented the project TIA. It's by Raluca Gainer, together with Simon Lucas and Diego Perez-Liebana. And they propose a continuously improving AI game player, which consists of a knowledge base in which it puts all the information of patterns that have been useful in playing a game. And this knowledge base itself is a pattern tool that can easily be applied if a new game is being presented. So the agent continuously receives new games that it shall learn, and it can rely on its knowledge base and advance on it to improve its learning behavior. And therefore, similar to me picking up a game of the same genre, I immediately know how it controls. I just need to learn how this specific game plays. And then I can really concentrate on not just improving the general pattern identification, but also on applying these patterns to play as efficient as possible and to just optimize those patterns such that they match the current game that I am playing. And the goals and visions that I have with this is to develop a self-optimized abstractions applicable to any game environment. They should be able to transfer skills, not just between multiple game instances, but between whole game genres. Because if I'm playing one jump and run, I'm likely to play the other jump and run as well. And I want to create a single agent that is capable of picking up any game and learning them quickly based on the experience that it previously gained, because this information is most likely also been used by human. We are such good pattern identifiers, and we can just reuse information that we have from our usual life experience. And therefore, I want to end my talk, and I thank you very much for your attention. If you want to search up any of my publications, you can find them on my personal website. And if you're interested in joining the Strategia project or basing your own work on strategy games, you can find the framework and related publications on the webpage on the right. Thank you very much. And I'm hopeful, I hope you have some questions, and maybe you are already eager to get into the coffee break.
Thank you, Alexander. It was quite a keynote. I'm opening the space for questions, either for the room or the virtual room.
I would like to ask Emmanuel, one question to Dr. Dockhorn. I would like to ask you what kind of approach can be used for using symbolic machine learning to inspect the decision process and abstraction and model learning.
Yeah. So what we've seen is if we implement a game, for example, we often have object descriptions already at our hand. So the game developer, for example, describes an object as stone. And if we consider such forward models like the local forward model, we can say that if the player is standing next to a stone, so player to the right of stone, and goes to the left, it is moving the stone and the player is moving. So we get an abstract rule of how these components behave, and the symbols basically represent the names or characteristics of the component itself. Now, this becomes more harder if we don't have background information to the objects, but you can think of, like, for example, a visual representation that is being analyzed, like in the Atari framework. We base our decisions on the pixel information. And there are many visual object recognition neural networks, for example, like convolutional neural networks that are just very efficient in labeling objects or identifying them. And then we could use this as an import for a symbolic system and make the output more readable. If we have an end-to-end forward model like a deep neural network, we could use rule induction mechanisms to find out what are the approximate rules with which the neural network is predicting the future state. And then we can once again apply these symbolic replacements, but they won't be perfect if we don't start with a symbolic system.
Okay, thank you very much.
You're welcome.
Any other questions for Alexander? Okay, from my side, Alexander, it was, I repeat myself, it was quite a presentation. I'm not quite involved in the AI studying, so it was quite an introduction to understand what is behind that, and you got with the strategy and the Atari, so I'm looking forward to understand more and try to collaborate with the Stratega project.
Thank you very much. That's the best feedback I could get. If you are interested and you don't know where to start, please contact me. We also have a wonderful community on Discord in which we frequently help others with getting started with the framework. And if you're interested in my work, feel free to contact me and we can have a chat anytime.
Thanks, Alexander.
Bye. Thank you very much
Okay.
for the invitation. I wish you all a wonderful conference and then a good coffee break.
Thank you, Alexander. So with Alexander's keynote, we finished the track for video games and gamification in the 2022 ARGENCON. I'd like to thank again Lorena, Carlos, Mario, and Alexander for the presentations and their works. And you may go to the coffee break. Thank you very much. Have a nice day.
Bye.
Bye-bye.